The Australian Institute of Physics, the Teachers Guild of New South Wales, the Royal Society of New South Wales, the Royal Australian Chemical Institute acknowledges the traditional custodians of the country throughout Australia. We recognise their continuing connections to the traditional lands and waters and would like to pay the respects to the elders, past and present. Ladies and gentlemen, my name is Dr. Frederick Osman. As the President of the Teachers Guild of New South Wales and the Secretary of the Australian Institute of Physics New South Wales branch, I'm pleased to welcome you here to the Concord Golf Club for the 2023 Frontiers of Science Forum presented by the AIP, the Teachers Guild of New South Wales, the Royal Society of New South Wales and Royal Australian Chemical Institute. Tonight, we are very privileged to be joined by our distinguished presenters, which include Honorary Professor Robert Boy, Dr. Anna Romanov, Associate Professor David Bishop, and Associate Professor Susanna Guatali as our speakers at this year's combined Frontiers of Science Forum event. Thank you also to our sponsors, including the Laboratories Credit Union, that are actually here today and also sponsoring this event for 2023. I would also like to thank Ian Wolfe from Diffusion Radio, who will be involved with our panel discussion later this evening on exploring major discoveries and theories in physics, mathematics, biology and chemistry. The format schedule of this evening will be our presenters to speak for 25 minutes, each on their chosen Frontiers of Science topics, and this will include with a panel discussion and Q&A at the end. So please hold your questions to the panel discussion session. We are also videoing this event so we can make it available for everyone that could not attend tonight. Without further ado, I would now like to invite the Emeritus Professor Ian Sloane, past President of the Royal Society of New South Wales, to provide the official welcome on behalf of the organising associations for the event. Thank you, Ian.
Thank you, Fred. Well, it's an enormous pleasure and privilege for me to welcome. I didn't know till I came that I was doing the welcome for all the organisations, but you know, it's all the better. So I am past president of the Royal Society of New South Wales, which is the oldest, I think, of the societies, and it's been more than 200 years old, and it has been giving intellectual encouragement, scientific encouragement since 1821. The first president was the celebrated astronomer, Governor Brisbane. You probably think he was a governor, but I think he was an astronomer. This Royal Society has continued to be active in promoting intellectual inquiry of all kinds, and in that way it's like this forum, which I think is a wonderful thing. Breadth, it covers so many areas, and I'll come back to that. I welcome you also on behalf of I see that the Teachers Guild of New South Wales itself has a venerable heritage, established 1892, which is really fabulous, and they do a great job, and we all know they're maybe the most important people in the room are the teachers. The Australian Institute of Physics, I'm a fellow of the Institute of Physics, so I feel strong warmth towards it. It's a wonderful organisation, and it also is keen to welcome you here. And RACI, the Royal Australian Chemical Institute, is a very internationally sort of important, significant body. And so it's really wonderful to see that the organisations come together. I thought I would just say a word about breadth. I really do think that breadth for scientists, for young scientists, to me, one of the problems with science, of being a scientist, is that the internal pressure is to specialise, to become more and more expert in less and less. And I believe that, Tibor is agreeing with me, I believe that this is to be resisted, you know, by individually and collectively. Try to be broad. Feel free to join the Royal Society of New South Wales, by the way. We welcome all comers. So I think I don't want to say too much because Robert Bowie is waiting to have his turn. So thank you very much. I welcome you, all of you here. Thank you for coming.
Thank you, Ian. So on behalf of the Australian Institute of Physics, the Teachers Guild of New South Wales, the Royal Society of New South Wales and the Royal Australian Chemical Institute, I would now like to introduce our first presenter, Honorary Professor Robert Boy, to open the presentation proceedings for the 4th Frontiers of Science Forum. Honorary Professor Robert Boy was until 2 years ago an NHMRC practitioner fellow focusing on the vaccine preventable diseases. His funding has exceeded $30 million from NHMRC, ARC, Wellcome, QATR, NRF, medical charities and industries, about 75 grants. He is a former co-director of NCIRS, recent chair of the Immunisation Coalition from the age of 37, and was a chair of HOD, Academic Child Health, Queen Mary, University of London. He has published over 350 times, especially in the fields of influenza, respiratory, viral diseases, over 100 papers, invasive bacterial diseases and COVID. For the past 5 years, he has consistently had 15 or more papers per year in the medical literature. Ladies and gentlemen, please welcome Honorary Professor Robert Boy.
Oh, thanks. Gosh, that was boring. I've got a Dutch name with 2 O's, so the way to remember my name is I'm a boy, I'm a big boy, and you pronounce 1 O. The Dutch always double up on their A's and on their I's and on their O's. So I've been telling people for over 50 years, it's boy, not girl. And it's a pleasure to be with you. I'm going to give you a bit of a rollicking ride, but I'm going to make it, I hope, accessible as well as inspiring and informing. And see if my slides work. So I work at the interface of a whole bunch of biological science and practical medicine fields, and I really enjoy interacting with all the specialists with whom I work. And I also interact with government. I've been an academic for over 30 years. I work with just about every vaccine company in Australia, so that's industry, and I do the occasional media interview. So this week in the Age and the Sydney Morning Herald, there's a regular feature called Examine, where scientists get a chance to look at, that's not me, is it? Scientists get a chance to look at issues dealt with by a top-level journalist who interviews the best in the field. And what came out this week was more information on where did the COVID pandemic come from. And it's, in simple terms, the Wuhan seafood market. And the Chinese led us to believe that they only had fish there, but everyone knew they had live mammals, animals. And they published mistakenly a paper earlier this month showing that there were raccoon dogs, and they found the DNA as much of the raccoon dog as they did of the RNA of coronavirus, and from the same sample. And there's lots of other reasons to believe that it was, we can't be definitive, but there's reasons to believe, without boring you, that there was a mammal interloping between a bat, where the coronavirus had come from, to a mammal, an amplifier, and then in the market, people got infected in the southwest corner. And when they looked at the samples, Eddie Holmes, who won the Prime Minister's Prize for Science a couple of years ago, said there was so much genetic material there, it looked like a bloody zoo. He's English, so he's allowed to say that. It's inexcusable, it's a bloody scandal. That the animal DNA was not mentioned first, they didn't find it, but his team did. They published it this year, and then it got withdrawn very quickly. So, probably a conspiracy. I call him Sherlock because he's gone into this to the extent where, as Sherlock Holmes would said, he's eliminated the impossible, and whatever remains, however improbable, has to be the truth. Okay, please. Okay, so this is a photo that he took 10 years ago when he went to the Wuhan market. And raccoon dogs were in close proximity with birds. And birds are also a conduit for viral transmission. And I'll tell you something more about that at the very end of my talk. So that's a raccoon dog. They can actually climb trees. It's not a dog, it's more like a fox. It's from the Canis family. And this is an editorial that we wrote and published only, a couple of weeks ago. I work with a virologist. I'm an epidemiologist, the science of public health. I'm into vaccines, I'm into infectious diseases, and so on. And I work with a retired TGA virologist, Gary Groman, and we publish every few weeks. And we said, is it really a lab leak? And we went through the evidence, and that was written a couple of weeks ago, published last week, and then the new stuff came out this week. Sorry, it's a little bit slow. So I posed the question: the Chinese have so much subterfuge and they're hiding so much. So who tells the truth these days? Maybe we also have a problem with telling the truth, but they certainly do. There's so much that isn't revealed. And please, one of my PhD students contacted me just over a month ago and said, here's a photo of my COVID rapid antigen tests, and that's why I'm not coming in this week. And I thought, well, there's no date on that. I'm a scientist. I want evidence, real evidence. So then I showed and here's my test. And I got positive too. I went on a plane in January, and I got off the plane 2 days later, I was positive. But there's no date on it, so you have to believe me. You have to trust me. And trust is important. Viruses don't live. We talk about proof of life, proof of viral life, but they're actually somewhere between live and dead in another state of being, because they cannot exist without another cell in which to divide and transmit. So plane trips are pretty dangerous. I've just got off another one today. The 2 times I've had COVID, in January this year and January last year, I just got off a plane. Dangerous places. Don't come too close to me. I call myself Astra Boy with 2 O's because I had 2 doses of Astra, and I've had 2 doses subsequently of Pfizer. For someone of my age with some medical issues and over 60, that's appropriate and that's effective. And I have what we call hybrid immunity, and that means a combination. Just as with animals, you crossbreed to get better hybrid strength. With your immune system, you can stimulate it with natural immunity on the back of vaccine-induced immunity, which is more systemic, but the natural immunity is in the respiratory area and helps to prevent you getting infection as well as more severe infection, more severe disease. Now, there's an alphabet soup of descriptions, and I'll just point you to the last line. We've had BA5 in the last few months, and the subsets of that have been XBB.1.5, and that's dominant right now. I call it extra bad boy, not because it's nasty to people, but because it transmits so easily, and it's a way to remember it. So if you are one of these people who have been a bit slow getting your 3rd dose, there's no doubt from the scientific evidence, from the statistical analyses, that the 3rd dose is highly protective against severe disease if you hadn't had a dose 6 months ago. If your 3rd dose was more than 6 months ago, I'd recommend getting your 4th. I certainly have had my 4th just before Christmas, and will have a 5th in a few months once I've lost the immunity from the wild virus infection I've had. No time to go into too much detail, so I'll keep going. I'm a paediatrician. I'm particularly interested in the health of children, but for 20 years I've also been interested in people's second childhood, and that means elderly people, and I do research on viruses in nursing homes, and we currently have some grants looking at how we can better detect and prevent influenza outbreaks in nursing homes. The latest data, cutting right through the COVID story to today, is that data from Europe, US and us indicates that it does seem to be on the retreat, and the pandemic is coming soon. The severity of COVID caused by Omicron variants is less severe, partly because of the virus, but also partly because we've got immunity. And that's both wild virus induced and vaccine. So the world is finally learning to live with COVID. The Americans, being financially minded as they are, have decided to stop buying doses for their population, but people who are insured, there's still 120 million doses available for them. So there's more than enough for people who need one this year. But from 6 months from now, August, September, they're going to start charging over $100 a dose. So once again, the haves will have and the have-nots will have not. And that's the American system. They think a lot of their own system, but the last line there, they think they're the best in the world. That's a Senate hearing only this week. And I point to the fact that they've had 1.1 million deaths, 5 times the rate of death that we have had. So we have done 5 times better at saving lives by rate of death from COVID that the Americans have done. And we're 5 times better than the UK as well. So this is where I live, in Kirribilli. And I make the point that it's said to be the most crowded place because we've got high rise. But it's not that crowded because you can see all the trees. But infections are driven in humankind by proximity, by crowding, as you very well know. And we've lived through 2 pandemics just in the last 15 years. I've been very involved with both of them. And there have been 7 public health emergencies of international concern in about the last 10 years. I'll describe what that is in a moment. These are all infections. So in 2019, before COVID had even been seen in any way, the WHO said the 10 biggest health threats were these. Can you see? Move around if you can't. I feel like I'm blocking you. No. Okay. So infections, health threats, not infection threats, health. And they include influenza, antibiotic resistance, Ebola, vaccine hesitancy, HIV. All of my favourite topics. And the WHO formally declares that if a situation is serious, sudden, unusual or unexpected, and has implications beyond a single country and its neighbours, then they, before going to a pandemic, they talk about a public health emergency of international concern. And here are some of them. You can see swine flu 2009, polio, Ebola twice. There's been 2 Ebola outbreaks in Africa. I'll talk a bit about those. COVID I've talked about. I've got a slide on monkeypox, but I won't have time. But so if you want to ask me questions later, I can tell you all the lurid details about Mpox, because it's not monkey, it's Mpox now, because we're very much into not being pejorative in epidemiology and in public health circles. And for some reason, people think that's pejorative. So now, in May last year, one particular country had virtually all of these diseases and more in outbreak situations. Ebola, COVID, cholera, Mpox, measles, plague, yellow fever, vaccine-derived polio. Now, what country was that, and would you like to go there on holiday next week? Well, do you know? It's in Africa.
Congo?
Well done. Yes, the Democratic Republic of Congo. Yes. So their emergency in 2019 was of Ebola. The WHO stopped saying, don't close your borders, because people then sneak through the borders unseen, and they spread infection anyway. So could it be brought under control? If we go straight to the bottom point, there's a vaccine that's 99% effective. And the vaccine for Ebola was proven very quickly to be highly effective, using exactly what we did to eliminate and eradicate smallpox, the only disease we've eradicated from humans. And that was ring vaccination. So when you've got a case, you find all the people who are contacts of them, vaccinate them, and then vaccinate the contacts of the contacts. And ring vaccination is very effective. That's how we got rid of smallpox. An Australian declared the world free of smallpox in 1980 to the UN Assembly. His name was Frank Fenner. He was a virologist. I met him. Wonderful man. He died a few years ago. Another disease apart from Ebola is paralytic polio, actually got from the vaccine. Because if you have poorly vaccinated people and polio gets into the population of children especially, they transmit, and they transmit to children who aren't vaccinated, so they have prolonged infection. And while a virus is dividing in your body, it mutates because it's got a half-life of a day or two or whatever, or even hours. So the virus changes its genetic form, and it can revert from being something that just stimulates your immunity to something which has become neurovirulent again. The genetics changes back to the way it originally was. So that's really a nasty thing which we don't want to see. Here's a success. In 1988, there were 1/3 deaths in the world, cases in the world, and we're down to, by 2018, to just 33. We've got recent problems. Don't have time to go into great detail, but 7 cases were reported only last week from Africa. Where do they come from? Yes, 6 of them. So it's a real soup. I've got a friend who does work in the DRC, and it's very challenging. There's militia, there's war, there's crimes of war that I don't need to describe. It's a problem. And what they've got now is, for the first time, a newly developed vaccine that's only been used for 2 years has reverted to neurovirulence. It was actually designed not to revert, but suddenly, having been used for 2 years in 28 countries, 600 million doses, it had a chain of transmission in unvaccinated people and reverted to neurovirulence. So 6 cases of polio. Paralytic polio occurs 1 in 1,000, so there must have been 6,000 cases at least of polio to produce those 6. Disturbing. I wrote a paper in the Lancet 6 years ago or whatever, that we were edging ever closer to eradication, and we've spent literally many millions. We've got down to a small number of cases, but we're just still struggling to actually eradicate polio. So those are the 10 biggest threats. I want to talk a bit about flu and give you the history first. Back hundreds of years ago, it was noted to be an epidemic disease, respiratory, and people in Italy thought it was due to the influence of the stars, the occult, and that was the source of disease. So influenza, influence of the stars, and it also came to mean an epidemic. And this is a virus that is really mutating fast in your body because it doesn't have good genetic mechanisms to proofread its progeny, so it makes children that look slightly different to the parents, and they go, "Hey, where'd you come from?" And so if you get 2 viral infections slightly different from 2 different people in one person, you can get a recombination of the genetic material, and that can produce a totally new virus, that recombination, called a shift, which is the cause of pandemics. Simple as that. So influenza went away during COVID because we had lack of social distancing, because we wore masks, because we washed hands, and because we had no one flying in from overseas for 2 years. We went from almost 1,000 influenza deaths in 2019 to only 37, dramatically lower rates of disease and death in 2020 and 21. And by 22, when we opened up our borders again and we stopped having social distancing and started having parties again, we're back up to over 300 deaths. But remember, in 2022, 15,000 people died of COVID. So put them into context with each other. So flu, actually, because we opened up in March, April, we had a gazoot of flu, and by the end of May, early June, we had an early season last year, and we're expecting it again this year. I'm going to keep going to keep you awake. I'm not going to tell you every point because I've got too much to say. So I got a call from an email from CNN just over a week ago about China saying that Wuhan now had a flu outbreak. And the authorities there said, "Oh, we're going to lock it down, stop people going to school and work," as they had done in other countries for a long time, the zero COVID policy. So he asked my comment and I gave him a written reply. But Xi'an, which is near Wuhan, the outbreak was in Xi'an, not Wuhan, excuse me. And Xi'an is where the ancient capital of China was, and where the terracotta warriors, and where the warriors had been there for literally hundreds of years. So I call them entombed, but actually they were quarantined, and I'll make a little allusion to that, because it was Marco Polo who came from Venice all the way across China to Xi'an and learnt about trade and brought things back to Europe. And it was contact between the East and the West in 1348 that first brought plague to Europe. And what they did in Venice was to say if any ship had disease, they had to fly a yellow flag, and they had to wait for 40 days for sick people to die or get better. And then they let them disembark. So that was called quarantagioni, or quarantine in English. So there's a really interesting relationship between past and present pandemics that you may not appreciate. Coronaviruses may have been contributing to or even causing pandemics long before this one. There was MERS, of course, in 2012, and SARS, the first one, in 2002, but long before that. A molecular clock analysis on a coronavirus discovered over 50 years ago, they've looked back genetically and they've estimated that it came out of animals into humans in 1350, the same time that we had bubonic plague. So there might have been a co-infection in some of those outbreaks. But here's something even more interesting. The Russian flu, and I'm not being pejorative, but that's what they called it in 1890. The Russian flu may actually have been a coronavirus that came from cattle, because molecular clock analysis, again, of the genetics shows that this virus, coronavirus OC43, came out of cows into humans in 1890, coincidentally when we had a pandemic around the world due to Russian flu. Now, we don't have any samples, so we can't say. What we're doing is looking back genetically, but we can't take samples from then to specifically and convincingly say this was this or that. But it's kind of fun to think, okay, so that we know that it came, coronavirus came from cows 1890. Well, cowpox was found in 1790 to infect milkmaids and protect them from smallpox, and it became a vaccine. BCG is a bovine form of TB, which was passaged in a laboratory for 13 years to make it attenuated and made into a vaccine in the 1920s. And we still use it today. So there's an interesting obsession that humans have that if disease comes from a cow, maybe we can work out how to prevent it by looking at the cow's infection. And just as a sort of a small segue, the gene sequence from influenza C strain has been found in a coronavirus. So not only can two different flu viruses interact, but even a flu and a coronavirus infecting the same person can lead to a new virus. Fascinating. So there are interactions between viruses and bacteria too, and they can be at a genetic level, they can be at an environmental level, they can be in the human body when they're infected. So in the Great Influenza and the Great War, which concluded in 1918, we had a terrible pandemic that killed 50 million people. What isn't as widely understood is that the interaction with flu in humans makes them highly susceptible to an invasive bacterial infection which causes meningitis and septicemia, rapid onset and high rate of death and complications, something I've been studying for the last 30 years. And we published last year in the Medical Journal of Australia that there was a close association in Australia between outbreaks of flu with outbreaks of meningococcal, and that concurred with work around the world. But it had first been referred to in the BMJ, the British Medical Journal, 100 years ago, and crowding was important. And they said in that paper, antecedent, if you'd had influenza, you were more likely to get meningococcal disease. This is an editorial that we had in January. Not only did disease rates go up once we opened up, but they also went up because we haven't been vaccinating as well around the world. So you've got less prevention. And so that refers to measles. So I'll let you read that. The non-pharmaceutical interventions are simply behavioural change, hand washing, social distancing, etc. And many viruses, not just flu, became absent or reduced for 2 years. But now they're on the attack. Now they're surging, and I'll show you a few of them. So all of these cockles, which are bacteria, have all surged in the last year in Australia. And all these R viruses, Rota, respiratory syncytial rhino, etc., have also surged in Australia to different extents at different times, but only in the last few months and year. So the fact that we didn't have immunity from lower levels of infection has stored up an immunological debt where lots of the population at different ages are now susceptible to infection that they haven't had for 2 years. And so I'll keep going. So this is what happens yearly. You have births, you have susceptible people who haven't had an infection, you have an outbreak, a seasonal outbreak of flu or RSV, and immunity improves, and then the same thing happens again. You have more births, and you get they're susceptible because they haven't had disease. And so, but then we had 2 years where births accumulated and got older. So we had cases not only in children, but in older children as well. And that's what we saw last year, and I think we will see that again this year too. So, segue into birds. Influenza, you get it? So these seagulls are currently being reported around the world to be carrying flu virus to other animals, but also being killed by it. Highly pathogenic avian flu. It was first detected in birds 25 years ago, and then 20 years ago the virus spilled over when there have been huge increases just recently, and then spread to mammals. So sea lions and dolphins eat dead birds sometimes. But it's also, so that's a pelican that was proved to be killed by avian influenza. And what do we care? Well, we care about the environment, we care about animals, we also care about the fact that bird flu might jump into humans. And that's what we're really worried about, because it is so pathogenic, you won't have 1%, 2%, but 10%, 20%, even 50% mortality. So there's dolphins that have got infected. So this is what's happened. In mink farms, they've seen the scientific suggestion that it's going from cage to cage through a respiratory route. Now that's the scary part, because normally you have to have very close contact and a high viral contamination. But if it can go through the air and then from one animal to another, it can then go to humans as well. And that's the real concern. The data is not convincing yet, but it's concerning. And they've actually culled tens of thousands of mink and shut down a whole bunch of farms in Europe. And there's a mutation that fits with a favouring of mammal-to-mammal spread. So it's concerning. Don't run away tonight saying, woe is me, the world is ending. It's not, honest, but if an animal eats a sick bird, there's so much virus in it that the scavenging mammals predate and can get very sick. So we need better strategies, and the strategy I'd like to commend is better surveillance and better genetic testing, and better epidemiology as well. There's only been under 1,000 human cases of bird flu, but half of them have died. Okay, I won't give you the... So the World Organization of Animal Health last month has said that we've lost 40 million domestic and wild birds since the outbreak first was kicking off just a year and a half ago. 200 million have been culled. There's been over 100 outbreaks in mammals, from birds to mammals. Okay, I'll keep going. This is a guy who really scares me. He's a big Dutchman like me. I was in a conference in Malta in 2011. He's a virologist. And very seldom do I sit in a conference and stay awake. But this time I stayed awake and I had a shiver down my spine. He described an experiment with ferrets, which are like mink, which were given avian flu. They manipulated the flu in the lab to get one or two mutations, and then they set up an experiment with ferrets next to each other in cages so respiratory contamination could occur. And by about the fifth or the sixth cage, they had a variant of bird flu that had 5 mutations and was spreading between ferrets. And ferrets are the example we use of what might happen in humans. They have similarity in their response and their involvement with respiratory viruses. So this guy is called Ron Fouchier, and he got into international and US controversy because he was doing what's called gain-of-function research. And that's exactly what people are worried about might have happened with COVID-19. And some people blame Anthony Fauci for giving US money to the Institute of Virology because they did do gain of function, where they looked at how you could manipulate the virus genetically to change its behaviour in the hope of getting ahead of it if it became a real problem. So I don't believe the lab. I don't believe the theory that it's gain of function, but it's something we've had to look at carefully and still are considering. So finishing. Many of you deal with the public, or you deal with your own children or your colleagues, and I'm a touchy-feely paediatrician, so what I believe in is if I'm trying to convince someone to get a vaccine, I listen to them first, engage them, talk about examples that are important to me. I highlight the seriousness of not vaccinating, the damage that diseases can do, and I don't confront people about their beliefs, their vaccine hesitancy. I take a softer route, and I'm just finishing now. So focusing the message on the safety of the child. So I'll go back to, I've been highlighting along the way what the WHO has been saying, and they've got a Director General who's been in place for quite a while. His name is Tedros Ghebreyesus, and you've seen him on the news and on the television many times. And he makes the point that together, if we could have sustained and combined political commitment to build health systems, especially in poorer nations, we can do public good. Vaccinations are one of the most powerful innovations in the history of health. Sanitation is perhaps only the more effective. And we must not take this scientific miracle for granted. Sorry for going over time. Thank you.
Okay, it gives me great pleasure to introduce our second speaker in the area of mathematics. Dr. Anna Romanov received her PhD in pure mathematics from the University of Utah in 2018, then immediately traded her mountains for beaches and moved to Sydney for a National Science Foundation postdoc fellowship at the University of Sydney. In 2021, she joined the School of Mathematics and Statistics at the University of New South Wales as a tenure-track lecturer. Her research is in representation theory, the mathematical language of symmetry. Ladies and gentlemen, please welcome Dr. Anna Romanov.
Okay, I'll attempt to juggle this microphone and pointer situation. Hello, it's so nice to see everyone. It's nice to see an audience full of faces. I know it's a big ask to come out and listen to a public lecture on math on your Friday evening, so it's really nice to have you all here listening to me. My name is Anna, and I'm a pure mathematician at the University of New South Wales in Sydney. And what I want to do today is I want to tell you about a powerful new tool at the forefront of my research area. This tool is something called categorification. But before I can get to that point, I have to take you on a bit of a journey. So what I want to do with you today is I want to take you through 3 different mathematical worlds. Some of these worlds will be familiar to you. You probably encountered them in school. But other worlds will be uncharted territory for most people in the audience. And once we get the lay of the land in these worlds, what I'd like to do is I'd like to ask this question that I have as the title of my talk. What does equals mean? And I want to try to show you that this question is more subtle and interesting than it seems on its face. Okay, are you ready? So I figured that I should start a math talk, at the place where we expect, which is an equation. So I'll give you a second to look at this equation and take it in. You might be having various reactions to it. Maybe it makes you nervous, gives you flashbacks to year 7 algebra class. Maybe you're excited because you know how to solve it and you like equations. But probably what you're not asking yourself is, what does it mean? Because it's clear to us what this means. It means, for what number x is 5 times that number plus 3 equal to 7? And the reason why this is unambiguous is because for numbers, we know what this word equal means. 5 is only equal to 5. 340 is only equal to 340. Pi is only equal to pi. So for numbers, equality is something we understand well. But is math only about numbers? I'll tell you guys a little secret. I don't actually like numbers that much, and I'm a professional mathematician. What I like are shapes and patterns, and luckily for me, these are also mathematics. So here's a familiar friend, which probably you encountered sometime in school, a triangle. And here's another one. So I want to ask myself the question about these two triangles. Are these two triangles equal? And actually, I don't want to ask myself. I want to ask you guys. So it seems like this is a time for some interaction. Let's see a show of hands. Raise your hand if you think these triangles are equal. I'm not trying to trick you. I also would raise my hand. I think these triangles are equal. In fact, I know they're equal because I got the second one by taking the first one and copy pasting. So these triangles have the same side lengths and the same angles, and so really they're on the nose equal. But what about these triangles? Let's take another poll. Raise your hand if you think these triangles are equal.
Could be.
Okay, yeah, I've got fewer hands. We got some good words coming out. So these triangles, they're not exactly equal. Like clearly the one on the right is bigger than the one on the left, but they have the same angles in their interior. And because of that, they share a lot of important properties. In particular, if we look at the ratios of their different sides, these are the same. And when we study triangles, we care about these ratios a whole lot more than we care about the actual side lengths themselves. And the reason for this is because these ratios are the building blocks for these trigonometric formulas that you learned once upon a time in a calculus class and had to memorize, like this one here, sine squared plus cosine squared is equal to 1. So in the world of triangles, we care about ratios of side lengths more than side lengths themselves. So when we look at these two triangles, we'd like them to be the same in some sense because they have these same properties. But we feel a little uncomfortable using the word equal, so we throw a new word on there, similar. We say that these two triangles are similar. In the world of triangles, equals means similar. Okay. Here's another world, one which probably you haven't encountered unless you've done maybe some university classes in mathematics, and this is the world of topological surfaces. So what are these? Topological surfaces are shapes which look locally flat. So what do I mean by that? I mean, if you were a tiny ant living on one of these shapes, and you could only see the area immediately around you, you wouldn't know that your world had any shape. You would just think that it was flat. So a topological surface is something that looks like this. Here are a few examples. We could take a two-dimensional plane. This is a topological surface because it's globally flat, and so locally it's also flat. But we could also take a sphere. We live on roughly a sphere, and we think, if we look out into the distance, that it's mostly flat. But you can have some more interesting characters, like the surface of a donut, which mathematicians call a torus. This is also a topological surface, because locally it looks flat. Okay, so this is an interesting new world of topological surfaces. And we can ask the same question that I asked about triangles. When are two topological surfaces equal? So here's two spheres. These ones are definitely equal, because I played the copy-paste game again. But say I was making these spheres out of clay, and when I made the second one, I wasn't so careful, and I left a little indentation in it with my thumb. These spheres are almost the same. There's only a tiny little dent which makes them different, and so should these be considered the same sphere, or should they be considered different ones? Well, I think that I only made a little mistake with my clay, so I think these should be the same sphere. But if I'm going to say that these two spheres are the same, with a little dent, then I have to allow for bigger dents too, because how do I determine what's the right size of dent to allow for? But then, if I allow for bigger dents too, then I need to allow for a lot more than dents. I should say that two spheres are the same if I can mold one into the other by stretching or twisting, as long as I don't tear it or glue it together. And I couldn't help myself here but have an interlude for a mathematical joke, because this is a great classic mathematical joke, and you can all know it now and take it home and tell people. What's the difference between a topologist and a barista? A barista is somebody who can tell the difference between a coffee cup and a donut. Because, let's see, to a topologist, they're the same thing. So with this notion of equality that I just described, you can take a coffee mug and you can continuously deform it until you get a donut. So topologists can't see the difference. This is a beautiful sculpture by Henry Segerman. Great. So back to our topological world. Again, we want to have a notion of equality, which we just described. Two things are equal if we can continuously mold one into the other without tearing. But we don't want to call it equal. We choose a new word. This time we choose the word homeomorphic. So two topological surfaces are homeomorphic if we can continuously mold one into the other without tearing it or gluing it. Okay, another world. Our third world I want to talk about today is the world of knots. Now, knots are something familiar to us. We have knots in three-dimensional space. Imagine we have a knot in a piece of string, like this. And I'm going to close up the ends of all of my knots. Mathematicians like to think about knots as closed things, and so I'll think about knots as loops like this instead of having strings that go off. And then I want to, again, ask the same question. When are two knots equal? Now, probably you have some opinions on this. If you thought about this, you'd think, okay, well, I have an idea of when two knots should be equal. I can have a knot in physical space, and if I can manipulate one knot into another knot, then those two knots should be the same. So for example, these two knots, I just took one and I added a little twist, but I could always untwist that. So these two knots should be the same because I can manipulate one into the other one. And this notion of equality makes a lot of sense intuitively. We can play with knots, so this is what it should mean for knots to be equal. But the problem is now it's a really hard question determining when a knot is equal to another knot. So here's two knots. The one on this side looks much more complicated than the other one. But are they equal? To tell whether or not they're equal, you'd have to say if you could manipulate the first knot into the second. And if you think they're not equal, you'd have to prove to me that there's no way you can manipulate the first knot into the second. And that's going to be pretty hard to do. So at this point in time, as we enter these different mathematical worlds with more relaxed notions of equality, suddenly questions that were obvious for numbers, when are two numbers equal, become interesting mathematical questions. Telling when two triangles are equal is a little bit harder than telling when two numbers are equal. Telling when two topological surfaces are equal is even more hard. And telling when two knots are equal is a notoriously difficult problem. So what do? We now have reached a fundamental question in disciplines across mathematics, which is this thing equal to this other thing? So, for example, is this triangle equal to that triangle? Is a coffee cup equal to a donut? Is a hard knot actually just equal to a loop? Now, how do we go about answering these questions? Mathematicians have developed techniques for answering questions like this in different disciplines, and the main technique they have is something called an invariant. An invariant is a measurement of a mathematical object that lets us determine when two objects are not equal. So let me give you a few examples. Here's an example with triangles. Triangles have three angles, and so one of those angles is the smallest angle, and this smallest angle is an invariant of a triangle, because if two triangles are similar, all their angles are the same, so their smallest angle is definitely the same, which means that if we have two triangles, like these, and their smallest angles are not the same, then they're not similar. So this invariant helps us distinguish triangles. But notice that it's a really rough measurement. Triangles have three angles, and we're only measuring one of them, so we're losing a lot of information when we just keep track of the smallest angle. But it still lets us tell when two triangles are different. Okay, what about topological surfaces? Here's an interesting invariant of a topological surface, which is a little bit more involved in the triangle one. How would we go about measuring one of these things? How do we measure a sphere? Well, here's a weird way you could do it. You could start by breaking it up into a bunch of little triangles. Here's how I've chosen to break it up into triangles. I have 4 triangles in the northern hemisphere and 4 triangles in the southern hemisphere. And then I can count these triangles in a strange way. What I can do is I can count the number of vertices. Those are the points at the ends of the triangles. And what would I get here? There are 4 vertices along the equator, one at the North Pole and one at the South Pole, so I have 6 vertices. Then I count the number of edges. There are 4 edges in the equator, 4 edges in the northern hemisphere, 4 in the southern hemisphere. That's 12. And then I add the number of faces. Faces are the triangles themselves. And so I get 4 in the northern hemisphere, 4 in the southern hemisphere, for a total of 6 minus 12 plus 8 is 2. So this is a way I can measure a sphere. I can say the Euler characteristic of a sphere is 2. Now I'm going to pause here because you all should be very suspicious of me at this point in time. Because at the beginning I kind of glossed something over and I said, oh, we just break the sphere into triangles and then we do this count. But what I hope at least some of you are thinking in your heads is you could break a sphere into triangles in lots of different ways. Like I just chose this one, but we could have covered the sphere in lots of really tiny triangles. And if we did that, we'd have way more vertices, way more edges, and way more faces. And so it seems unlikely that we would still get this number 2. But something that's really beautiful about the Euler characteristic is you do. And I really encourage you to try this at home if you want to, or try this the rest of the talk if you're bored. Take a sphere and break it up into triangles, however you'd wish, and do this count. Count vertices minus edges plus faces, and convince yourself that no matter how you break it into triangles, you always get the number 2 on your sphere. And so this thing gives us a way to measure a sphere. It's an invariant. And this helps us to tell when 2 topological surfaces are not homeomorphic. So if we played the same game with the torus and we broke it up into triangles and did our count, we would get 0. We wouldn't get 2. And so that tells us the sphere and the torus are not homeomorphic. But again, this measurement is a little bit crude. It doesn't tell us everything about the sphere. In fact, we can have different topological spaces that have the same Euler characteristic. So if we took a Mobius strip, that's what we get if we take a strip of paper, twist it one time, and glue it back together. This thing has an Euler characteristic of 0, which is the same as the torus. But they're not homeomorphic. So the Euler characteristic isn't a perfect measurement, but it's definitely a start. Okay, so what we've seen so far in these examples is that we can try to answer our equality question by finding invariants, but one invariant's not going to be enough. If we want to answer the question, we need to find lots of them. And so our new goal becomes find as many invariants as possible in our specific mathematical world to try to tell when 2 things are equal. And this game of finding invariants becomes the life work of many mathematicians. And it's hard work. How do we actually do it? The example I gave you of the Euler characteristic was very strange. Like, how did I come up with that measurement of a sphere? And say I'm in some other mathematical world, like the world of knots, how do I come up with a measurement of a knot? And finally, this brings me to the idea at the forefront of my field that I wanted to talk to you about. And this is a mathematical machine for coming up with invariants. And it's something called categorification. Okay, so at this point in time, my talk is going to get a little bit more abstract, so I want to start by giving you the idea of the machine before I get into the mathematical details. So the idea of categorification is that sometimes what we're seeing mathematically is just a shadow. And if we can realize this, that the thing we care about is a shadow of something else, then suddenly we gain additional insight that we didn't have before. And we can study the thing casting the shadow instead of the shadow itself, and this is very useful. So, what casts shadows in mathematics? The thing that casts shadows is something called a category. Now, in mathematics, the name of our game is to generalize things. We don't want to study examples one by one. We want to build general machinery and universal axioms that can describe lots of examples at once. In essence, this is what mathematics is. And a category is an especially useful general concept that encompasses almost all of mathematics at the same time. So what is it? What is a category? Well, a category consists of 2 things. It consists of objects, some collection of objects. These could be knots, these could be topological surfaces, these could be triangles. I'm just going to draw them as dots because I don't want to specify what they are. They could be anything. And then a category also consists of something called morphisms, which I'll draw as arrows between my dots. And morphisms are ways that we can go between different objects in our categories. So I've already shown you a picture of a morphism in this talk. I showed you the picture of the coffee cup turning into the donut. And so this is a continuous transformation of a topological surface, and so that transformation should be one of the arrows in my category. So the thing about categories, the great idea here, is that if we keep track not only of the things that we care about, the objects, but if we keep track also of how they're related to each other, this is very powerful. So let me give you an example, because I know that that's a very abstract idea. So here's a category, one of my favorites, the category of vector spaces. So perhaps you've heard of vector spaces before, perhaps you haven't. The objects in this category are vector spaces, and I think you've encountered them even if you haven't heard the word before. So vector spaces are things like lines, a one-dimensional line, or planes, a two-dimensional plane, or three-dimensional space like the space we live in, but they can also be much bigger. We can have a 40-dimensional vector space or a 300-dimensional vector space. And my dots, my objects, are going to be all vector spaces. My arrows, my morphisms, are matrices. So you've surely seen matrices before at some point. Maybe you think about them as just arrays of numbers, but mathematicians like to think about matrices as transformations of vector spaces. We can take a matrix and multiply it by a vector, and we get another vector. So that means that a matrix is a function between vector spaces. Okay, so this is a very nice category, but I've taken a big detour here. What I want to tell you about are not categories, but categorification. This word has categories in it, and so surely it has something to do with categories, but what actually is it? Well, the idea behind categorification is to take something simple, like a number or a polynomial, and replace it with a category. And we should do so in such a way that we can always go backwards. There should be some way that we can get back to our number or our polynomial from the category. And here I'd like to pause again and point out that this is a really strange idea. So a number is something you're familiar with, it's concrete, it's something you've thought about before. A category was very abstract. I just gave you this crazy abstract definition, and so we took something simple and made it more complicated. Why would we do this? Why would it be useful to study something by making it more complicated? And the idea is the shadow analogy that I gave you earlier. So the number, the polynomial, sometimes it's just a shadow, and if we want to understand that shadow, we can replace it with the thing casting the shadow. Even if it's more complicated, this is still going to be useful. Okay, let's see an example. So here's something relatively simple, the natural numbers, the numbers we can count with, 0, 1, 2, 3, 4, 5. These have a categorification in the category of vector spaces. And the way we go backwards, how we recover numbers from vector spaces, is by taking their dimension. Every vector space has a dimension. A plane is two-dimensional, a line is one-dimensional. So if you hand me a vector space, I can get a number from it by taking its dimension. And the idea here is that numbers are shadows of vector spaces. So sometimes a number is just a number, and we think about it that way, but sometimes a number is measuring something. Sometimes it's measuring the dimension of a certain vector space, and if we have that additional information, that it's measuring dimension, suddenly it's much richer than just a number. It has meaning. Okay, so I've taken you on a long journey. Let me do a quick recap of what I've done so far. What I've done is I've given you a few mathematical worlds, which I like, worlds that are not numbers, and I've asked a question, how do we know when two things are equal in these two worlds? And I told you that invariants were a good way to figure this out, but they were hard to find, so we needed as many as possible. And then I introduced this big abstract machine, categorification, which is supposed to help us find invariants. But the last thing I haven't done is I haven't told you how. So I haven't told you how categorification actually helps us. So that's what I want to end with in my last few minutes, how categorification helps us find these invariants. So let's look at our topological surfaces example. Here, I gave you an invariant, the Euler characteristic. And it turns out that this has a categorification in some category called the category of graded vector spaces. This is similar to the category of vector spaces I described, just a little bit more souped up. And there's a natural way we can take one of these graded vector spaces and produce a number, the Euler characteristic, by taking the alternating sum of dimensions. So the Euler characteristic is a shadow. It's a shadow of this category of graded vector spaces. But this category is rich. It has all sorts of things going on besides this one number. And so if we look to the category, we can discover other invariants by looking at different versions of the graded vector spaces. Instead of taking an alternating sum of dimensions, we can just take dimensions themselves, and we get a whole host of new invariants, which are called Betti numbers. So the takeaway from this is that by realizing the Euler characteristic as a shadow of a category, we gain a whole new collection of information, and this helps us answer our equality question, for this specific case of topological surfaces. Okay, so we ramped things up really quickly there. But what I hope to have done is I've shown you one example of categorification. There are dozens of others examples of how it's been useful in mathematics in recent years. And there's a really beautiful one with knots in the Jones polynomial, which unfortunately I don't have time to talk about today. But if you want to ask me questions later, I'm very happy to. And what I hope for you to take away from this is just to get a little glimpse of my mathematical world and the way that mathematicians think. And maybe my lesson for you is to always look beyond the shadows. That's all I have. Thank you. Maybe.
Before we take our short break as halfway point, I'd like to introduce to our event our main sponsor, Sally Boswell, Business Development Manager from the Laboratories Credit Union, LCU, to come forward to introduce LC to us. Please come forward.
Just some background on Laboratories Credit Union. We were set up by CSIRO staff 60 years ago, and we're a member-owned financial institution. We have all the services offered by the bigger banks, but with the service levels that's often forgotten these days. We support the science community through the CSIRO Alumni Prize, AIP and RACI, along with scholarships for our younger members. So if you're looking for a mortgage, savings accounts, fixed-term deposits or kids accounts, or just had enough of your current financial institution, stop by and give us a call. Or you can stop by and have a chat with me this evening. Thank you.
Associate Professor David Bishop is an Associate Professor in Analytical Chemistry at the University of Technology, Sydney, where his research focuses on the application of the state-of-the-art technology to analytical challenges in a diverse range of disciplines, with a particular emphasis on biological and environmental sciences. David has spent 12 years' experience in developing teaching and undergraduate analytical chemistry subjects, and in 2023 introduced a Masters in Science major in Analytical Chemical Technologies. His teaching has particular focus on gaining hands-on experience in modern analytical instrumentation and its appropriate use in a wide range of disciplines. He has mentored undergraduate research interns, honours students and PhD students during their degrees. And he takes great pride in seeing them apply their theoretical and applied analytical abilities to transdisciplinary tasks, providing them with skill sets that will suit future careers in industry and academia. Ladies and gentlemen, please welcome Professor David Bishop.
Thanks for the introduction. So, as Fred said, I'm an analytical chemist. So what does that mean? Well, I can tell you the composition of stuff. So what that stuff is depends on what you're interested in, whether it might be looking at trace contaminants in environmental samples, to we heard before about viruses, developing new tests for virology as well. Now, I have a particular interest in technology and applying that technology, and my main research focus is on elemental analysis. So we heard before about Eddie Sherlock Holmes. Well, I'm not answering, the answer isn't elemental. I'm using technology to answer the elemental question. So do I want to know about elements? First off, what do you know about lead? I took way too long trying to find a good picture from the castle. It's not possible. It's movie's too old, hadn't been done up in high definition. If you wanted to know about lead in your soil these days, you'll be using a piece of technology called, in most cases, inductively coupled plasma mass spectrometry. And that is what I'm going to be focusing my talk on today. So we can measure elements in a number of ways. So I know that there are school teachers here today, and if you teach high school chemistry, you might learn about atomic absorption spectroscopy or atomic emission spectroscopy. That technology is a little bit out of date by about 20 years. If you're trying to determine elemental concentrations these days, you're most likely going to be using what we call an inductively coupled plasma mass spectrometer, or ICP-MS. So what I'm going to do today is I'm going to provide to you an overview of the technology, recent advances in the technology, and I'll spend the second half of the presentation giving some uses of the technology as well. Mainly research uses, because the fundamental uses in clinical, so this technology is very widely used. You go to any environmental testing laboratory, they'll have a number of these. You can go to the clinical pathology labs, they have these instruments. They are very widely used across industry in New South Wales and Australia. So first off, what is an ICP-MS? So an ICP consists of an inductively coupled plasma which evaporates, atomises and ionises whatever I put into it. So it's designed for aqueous sample introduction. So we introduce it as a liquid, and we have to get it into an ion form to be analysed by a mass spectrometer. So what is a plasma? So a very obvious example of what a plasma is, some of you may not know this, is the surface of the sun. So a plasma is an ionised gas and often produces high heat as a result of the ionisation process. The surface of the sun is about 6,000 Kelvin. The temperature of an ICP plasma is around 6,000 to 10,000 Kelvin, depending on the parameters you're using. So inside this instrument I'm using is a source of heat which is hotter than the surface of the sun. And the whole point of that is to produce ions, and these ions then go into the mass spectrometer for analysis. So this technology was invented in a research lab in 1980, and its utility was very quickly recognised by two different manufacturers. So the first commercial instrument was produced in 1983. So from invention to commercial product, that's a very rapid time frame because it was seen as a significant advancement on what was available at the time. So how does an ICP-MS work? So as I said, there's two parts to it. There's inductively coupled plasma and a mass spectrometer. So inductively coupled plasma, first off, we need to create that plasma. So we have a stream of, does this work? Not really. Stream of argon gas which flows through this concentric torch area here. We have a radio frequency coil which produces high energy, and it's this radio frequency energy which actually ionises the argon flow. So basically, the ionisation process, this radio frequency source knocks an electron out of an argon atom, which then knocks more electrons out of other argon atoms to create this plasma. And as I said, it's in this plasma zone somewhere between 6,000 to 10,000 Kelvin degrees, depending on whereabouts in that zone it is. We then introduce our sample through the middle here, and as it goes through that process I talked about before of evaporating off all whatever your sample is carried in, whether it be water or normally some sort of weak acid solution, and then it atomises them, so it gets individual atoms, which are then ionised before it reaches the mass spectrometer. Then as it reaches the mass spectrometer, it goes through a series of electrostatic lenses, basically so anything which isn't ionised basically will sort of run into a stop and not go through into the mass spectrometer, because if it's not ionised, it'll go straight through the mass spectrometer and basically ruin the detector at the other side. And what do we get at the other side? Well, we end up getting if we have a ionic sample at this stage, we get something which a nice steady signal looking like this. Now, this instrument, we can analyse almost every element in the periodic table in a single analysis. And so let's say I'm looking at metals in seawater or some sort of sediment sample. I can look at 60, 70 elements in, let's say, 3 minutes per sample. It actually takes longer to clean the tubing between each injection than it does for the actual analysis in that sort of circumstance. So what is the mass spectrometer? So the mass spectrometer we use here is what we call a quadrupole mass spectrometer. So it consists of 4 rods, and these rods are set so at a certain voltage, only one ion will go through at a time. So this is what we call a scanning instrument. So these rods will then change voltage, and the next ion will go through, and so on. Now this is a pretty rapid process. depending on the type of mass spectrometer you're using. This can happen, 100 or so times a second. As it does depend on the mass spectrometer you're using. In ICP, we tend to spend about 50 milliseconds per ion tends to give us good sensitivity. So it's still a very rapid jump. And this is sort of just an example of what's happening when the voltage is not set for the ion, for a particular ion. You'll see it gets ejected out the sides, where only one ion, which is matched to the voltage of these rods, will go through to the other side. Now, after it passes through these rods, it goes to an electron multiplier. So what happens here? So we don't actually detect these ions. These ions will go through and hit a dynode and cause a cascade of electrons. So you'll see from a single ion hitting it, we get a massive cascade of electrons, so it actually multiplies the signal a lot as it goes through. It makes this a very sensitive technique. Under the right circumstances, you can detect down into the picograms per litre. So an idea of what a picogram is, it's a lot of zeros before you get to what you're measuring. So, as I said, it can detect almost everything in the periodic table. One of the reasons why argon is used, I mentioned it's an argon plasma, is basically because it will ionise almost everything else in the periodic table apart from a very few elements. Now, this table isn't really that accurate. Like, we theoretically can measure some of these, but they're just so common we can't separate, nitrogen and oxygen from what's naturally there. So even though, if we've got our sample in water, we can't really measure oxygen because it's part of our sample. The only ones we really can't measure there are sort of neon and fluorine, and obviously these ones which don't exist outside of certain radioactive laboratories. Now, with every piece of technology, there's always a but, right? What is it about this, fabulous technology which can detect all these elements at very low levels? There's always a but. The but for ICP-MS is interferences. So I said we're detecting ions. Most elements consist of more than one isotope. So, and these isotopes may overlap with each other. So a classic example for ICP-MS is calcium. The major isotope of calcium has a mass of 40. Argon, the gas we're using, has a mass of 40. So we can't really detect calcium at its major isotope. We can also get what's called doubly charged species, where theoretically we only want one electron to be knocked out of all of our elements as they go through into the plasma. One of the reasons why argon's a good plasma source is it normally only knocks out one electron. Sometimes 2 electrons will get knocked out. So what is actually measured is what we call a mass to charge. So if it's the mass over 1, as in 1 electron's out, it goes through at its nominal mass. If 2 electrons are knocked out, it goes through at half its mass. So we see things like barium is actually one of the few elements which does form doubly charged species relatively easily. It can interfere with gallium. The other major source of interference, and I'd say it's probably more of a problem than the doubly charged ones, is what we call polyatomic interferences, where basically 2 atoms will join together and ionize and then come through at a similar mass to what you're interested in. The major isotope of iron, iron 56, it's about 96% abundance out of all the isotopes of iron. It coincides with argon oxide, which said we've got an argon plasma, we're introducing our samples in water, it forms quite readily. So we sort of see, here's a few other examples where, so silicon 28 comes out at the same mass as N2. And I mentioned calcium before, I mentioned iron. Selenium is another one which is a little bit difficult to detect. So basically it's an argon dimer. It equals mass 80, which is the main isotope of selenium. Selenium also, other issue with selenium is its other major isotopes. Argon dimers also form for its other major isotopes. So it's a bit of a difficult one, but I'll go through some of the technology we have which allows us to still measure these sort of elements. the first bit of technology that was developed was the collision reaction cell. It's been in use since about 2001. And it does exactly what its name suggests. It either uses collisions or reactions to remove these interferences. So if we're using it as a reaction cell, you can see in the top example here, basically a charge is being transferred from an unwanted interference to something which won't interfere with our analysis. Something else won't interfere with our analysis. The most common way it's actually used is as a collision cell, where basically these, what we call polyatomic ions, they're big. They're really big and bulky compared to a single ion. Basically, they have that much collision inside this cell here, they slow down, so they don't actually have enough kinetic energy to make it through into the mass spectrometer. And that works for the majority of issues we may experience with this sort of technology. Now, this works quite well for a lot of things, apart from selenium, that I mentioned before, the iron oxide, the iron, and something like arsenic as well, which is a very commonly analysed element, because arsenic is obviously quite toxic as well. And technology was introduced in 2012. It was ICP triple quadrupole mass spectrometer, which what that does, it has an additional quadrupole in front of the collision reaction cell. So what that allows us to do, remember before I said that we can set the mass spectrometer so only one mass to charge, one ion goes through at a time. What we do is we can set it up so only that single ion goes through, or that single mass to charge goes through at a time. It then goes through into a reaction cell where we can either react away the unwanted products and they disappear, or we can, alternatively, if we can't react them away, we may be able to force a reaction of the ion we're actually interested in, so we can react it with something like oxygen to move it away again. So these two types of modes of analysis, as I said, we call it en masse, where we react away the unwanted interferences, or we do a mass shift where we react the ion we want to measure to a different mass, which has a different mass from its these interferences. And this, once again, works very well for the majority of analyses we want to do. But there are certain, I mentioned before that quadrupole mass spectrometers are what we call scanning instruments. There are certain circumstances when we don't want to do scanning. I'll go through application, what they may be in a few slides' time. And you may want to analyse everything coming through simultaneously. So a more recent advance is a ICP time of flight mass spectrometer, where a time of flight mass spectrometer, basically all of our ions of interest enter this, we call it a time of flight tube. They're accelerated in this flight tube, and their speed they go through that flight tube is dependent on their mass. So this is a high resolution instrument. By that I mean it is quite good at separating out all the ions from each other, but it has, and it's a simultaneous analysis. So it's much faster analysis. So I mentioned before 3 minutes for 70 elements, something like that. This is, it all happens at exactly the same time. So it's much faster, which is advantageous for some reasons. I'll get to that later. But it also has its disadvantages. If you have something which is of very high abundance, let's say argon again, or iron, and you're trying to analyse manganese, you can get sort of signal swamped across the detector. So it's not perfect, and it's also not very good for low-end, low-mass elements. So the most recent instrument which came on the market, came out last year, I think it was, they don't even bother looking for anything below mass 23, which is sodium. So there's a whole lot of elements which people are interested in below sodium, obviously, like boron, lithium. Lithium's obviously a big one at the moment in Australia and around the world with battery technology. Don't even bother with it. There's another instrument which is out, they don't even bother looking at anything below mass 103. They figured some of this stuff is too hard. But this is where, so this is very recent technology, and this is where the most advances are being made in this area, and I'll show you why it's needed shortly. Now, I did mention that it's designed for aqueous sample introduction, liquid sample introduction. That's quite easy. Basically, we nebulize it. Anything which is less than 10 micrometers, we have these devices which will separate out the stuff which is less than 10 micrometers to go into the plasma. Everything which is larger goes to waste. By everything which is larger, that's about 95% of the sample. Despite the fact that 95% of our sample goes to waste, and I didn't mention it before, but only about 0.01% or lower of what actually gets into the plasma makes it through to the detector, it's still a very sensitive technique, and it's a very robust technique. But what if I have a solid sample which can't be dissolved? What if I'm in the minerals industry and I'm trying to characterise the composition of my diamonds or something like that? Or I need spatial information. What if I'm trying to determine whereabouts some particular metal is located in a different disease state and trying to understand the biology of what's happening? We use a technique called laser ablation to allow us to sample solids and develop these give us these spatial information. I'll go a bit more into this process shortly. Another big challenge for analytical chemists these days is what about nanoparticles? Everyone's concerned about nanoparticles. How can we measure nanoparticles in environmental samples? How can we actually, and biological samples, how can we determine how prevalent they are and find out more information about them? Now, a very recent technique is called single particle ICP-MS, allows us to determine the size of nanoparticles in a sample as well as the concentration, and I'll briefly touch on that as well. So, very quickly, laser ablation, I mentioned minerals, that's where it was sort of first developed, trying to get, a lot of minerals are very hard to make aqueous. You've got to use stuff like hydrofluoric acid, which people don't want to use for some reason. It sort of melts everything. So they use they developed laser ablation ICP-MS to analyse the composition of minerals. The field was really taking off is elemental bioimaging, which allows us to quantify the spatial distribution of metals in various biological tissues. And when it's been around since about 94, but it started really taking off in the early 2000s. Laser technology used to be quite crude. So what you do is we hit a sample with a laser, it ablates a small amount of material which is swept into the plasma to go through the atomization, ionization process. Traditionally, the lasers used to be able to get sample resolution of 20 to 100 micrometers per spot size. Now there's been, in the last couple of years, been recent advancements in both laser and ICP technology. ICP, I'm talking about the ICP TOF, which has allowed us to now get resolution down to 1 micrometer, which is now down to below the size of a single cell. So how does the process work? Well, I scan my laser across our sample. Only the very recent lasers, I had a new laser installed 2 weeks ago. It can scan at 400 micrometers per second. That's where you need something like an ICP TOF, because your quadrupole ICP-MS cannot keep up with that sort of scan speeds. For each line which is scanned, produces a CSV file. We get a number of these CSV files across our brain. We get a line scan looking like this. We collate them all into a single file, and then we can create an image out the other side. We can run standards of the same time, so we can quantify the levels of metals in these images. Now, this is standard. We've been doing this sort of thing for a long time. So I first started doing this, I started my PhD back in 2007. But it's about sort of 2004 onwards, a lot of this work has been going on. It really sort of opened up the field of what we call metallomics, looking at the metal profile inside cells, inside biological organisms. Now, I use this standard sort of elemental imaging to look at presence of toxic metals in neurological diseases. Most neurological diseases, only about 10% of them have a genetic factor. Most others, they say they have an environmental factor. So I've been doing a lot of work looking at mercury in different diseases. So this is mercury in the locus coeruleus, which is at the sort of base of your brain. Actually co-localizing, so mercury top image, aluminium bottom image. So this is in the specific neurons in your brain. We found mercury in other neurons in the brain. So we had a whole heap of brain samples from, these are human brain samples, people who died with Parkinson's disease, people who just died with known amounts of mercury in the system, and people who died from other ailments. In one region of the brain, so this region at the bottom of the brain, they all had, every single person we looked at had mercury here, but it was only the people with Parkinson's had mercury in the regions of the brain where cell death occurs in Parkinson's. So there's some other factor which is taking mercury into those locations. Similarly, we can say the same thing about multiple sclerosis. So multiple sclerosis was actually interesting. We went there looking for mercury. Instead, we did find mercury. We also found an awful lot of silver. Silver is another toxic metal, widely used these days as an antimicrobial nanoparticle. You can find it in socks, dishwashing detergents, all sorts of things. But we haven't seen this in other, we didn't see this in Parkinson's, but in multiple sclerosis samples, silver was always present, as was mercury, and sometimes you see lead, we see other toxic elements as well. Once again, in our controls, in some certain regions, we saw the same pattern where mercury was also present, but in the multiple sclerosis samples, mercury was associated with the cells where damage is occurring. Now, this is all well and good if we're looking at sort of either metals which are supposed to be there or metals which aren't supposed to be there. What if I want to extend this to imaging biomolecules? What if I want to extend this to imaging proteins? Well, this is something which is only be less than 10 years old. A recent field we call immunomass spectrometry imaging. So immunomass spectrometry imaging allows us to quantitatively image protein expression by labelling these biomolecules with metals. So most proteins, in biology, they do these imaging processes called immunohistochemistry, where they apply antibodies which are raised to recognise a specific biomolecule, and then these antibodies are tagged with some sort of visualization reagent so they can be viewed through a microscope. So instead of tagging with either fluorescent tag or other visualization tag, we tag them with metals instead, which then allows us to use this technology I've just described to quantitatively image these biomolecules. Now, your typical immunofluorescent tag or other chromogenetic tag, it's not actually a quantitative technique. This is why if you know anyone who's had cancer or you've had cancer yourself, you get diagnoses 1+, 2+, 3+. That relies on very expert opinion, but it's a subjective analysis by the doctor looking at your sample. And that's why if you get multiple opinions, you often get, especially ones at the borderline between 1+, 2+, 2+, 3+, you get differences in what you may be graded. This technique is quantitative. Also, it allows us to look at multiple elements at the same time because ICP-MS, we can look at a large range of elements. Now, more commonly, people used to use fluorescence detection. Fluorescence is a big overlap between different fluorescence wavelengths, whereas with our ICP-MS, we can look at a large number of them. And particularly, once again, if we're scanning very fast, an ICP-TOF is incredibly handy. Now, I've used this to look at Duchenne muscular dystrophy. I'm not going to go into this slide, but basically it's a terminal childhood illness. People who get Duchenne muscular dystrophy, disease affects boys. They're usually wheelchair bound by the time they're 12, average lifespan about 20. Basically, their muscles waste away, and treatment's very hard for them to find. And the way they diagnose it, they use these, once again, subjective tests. So we went through and analysed dystrophin in healthy human, mild case of DMD, and the cases, the severity increased as we went along there. And our results matched up perfectly with clinical diagnoses, so showing the utility of this technique here. Where a TOF, I was only looking at one label there. Where a TOF really comes in handy, if you want to look at a large number of elements at once, that's where that quadrupole is very limited, and is where the TOF comes in. So also, as well as I mentioned before that the instrumentation's really changed, so the speed that the laser scan is improved dramatically, as well as how long the sample takes from the laser to the ICP has increased dramatically as well. So that's where the ICP-TOF can analyse all these elements at once. And there was a field called imaging mass cytometry, which some of you may or may not have heard of. It's basically a variation of this. It was developed to take advantage of this technology. And basically, there's one guy in Switzerland. He's been leading this field. He's really focused on cancers and breast cancer in particular, and he's using it to look at all sorts of diagnostics or components of cancer, looking at the environment of the cancer cells, the immune response cells, association between microenvironments. I won't go into it too much. Here's an example of what his data looks like. I'm not going to go into that either. But basically, they're sort of clustering different cell types together and sort of seeing how these cancer cells impact their environment. Now, I did mention I'll very quickly get onto single particle ICP-MS, which allows us to determine nanoparticle size and concentration. Now, once again, this is an area where the ICP-TOF, the recent advance in the field, comes in handy. Now, when we're using a quadrupole, I showed this figure before. When we have an ionic signal, we've got a steady ionic signal like that. Now, when we're measuring nanoparticles, they come through as a clump of ions. When we set our quadrupole parameters right, we can sort of still get something like this. What you're seeing there is basically each pulse above the noise here is a nanoparticle coming through. So we can count the number of nanoparticles coming through, and the size of the height, the size of the peak determines the size of the nanoparticle. So some of my colleagues who did a survey of Melbourne waterways where there's a history of lead contamination. Looked at 63 sites. They found lead across a large number of the sites. They also found titanium, so lead nanoparticles at most sites. They also found titanium nanoparticles at most sites as well. The titanium was somewhat interesting in that the blue line here is the average size. Most of the titanium nanoparticles are the same size, where lead was much more variable. Now, 63 samples, looking at 2 different nanoparticles, just about out of time. That's a lot. You have to do separate analysis for lead and for titanium there. That's a lot of analyses. So we can also look at microplastics and single cells. Where the TOF comes in, ICP TOF mentioned before, we can look at all the nanoparticles at once in the same analysis. So here's an example of sort of a mixture of silver and gold nanoparticles, and some of them are mixed silver and gold nanoparticles, and that's what we're showing there. And here's another sort of example there. So I think I've just got right on time. So hopefully what I've shown you today is that ICP-MS is a powerful multi-element detector. It can be used for aqueous and solid sampling as well as for nanoparticle analysis. And recent advances in technology have really allowed us to increase the number of analyses we're doing this to include stuff like nanoparticles as well as those highly multiplex biological applications, which are increasing the knowledge we have about cancers and other diseases. All right, thank you.
Our fourth and final speaker is in the area of physics. Associate Professor Susanna Guttali, awarded a PhD in physics at the University of Geneva in 2006. After a few years as Research Fellow at the Italian Nuclear Physics National Institute and at the Australian Nuclear Science Technology Organisation, she became an academic at the School of Physics and the Centre of Medical and Radiation Physics at the University of Wollongong. Susanna is an international leading expert of radiation transport simulation, software tools for radiation physics when applied to biomedicine, including irradiation, protection in Earth labs, aviation and space. In 2021, she was awarded the prestigious Women in Physics Award of the Australian Institute of Physics, which celebrates female physicists that gave a significant contribution to research in physics. In 2022, she became a member of the ARC, the Australian Research Council panel of experts. Susanna is very passionate about the public outreach activities aimed at to inspire the study of physics among the young generations. Ladies and gentlemen, please welcome Professor Susanna Guttali.
Good evening. Thank you for having me tonight, for inviting me to speak. A human mission to Mars has been identified as, let's say, one of the main goals of the human exploration of the solar system, isn't it? The roadmap started with the International Space Station. I'm sure you know about it. It's this incredible lab that rotates around the Earth and houses many experiments that go from physics to material science. It hosted more than 2,000 scientific activities, and let's say research there is performed to study processes and technologies to allow astronauts to stay in long-term space missions. Before going to Mars, well, maybe it's better to go to our beautiful natural satellites, the moon. The Artemis mission is envisaged for 2024, but in the long-term plan, the idea is to build a permanent lunar outpost to conduct research, again, to study processes and methods, technologies that allow a long-term stay of astronauts in space. Keep into mind that usually astronauts stay about 6 months on the International Space Station, and 12 astronauts have been on the moon, walking on the moon, and the missions to the moon are just a few days. A human mission to Mars is envisaged for the next decade, and it's a round trip. There are various mission scenarios. Let's say that a mission to Mars in total will last 2 or 3 years. So it's about 7 months to reach the red planet. Then the astronauts spend about 3 months at least to do research, and then they have to come back. But there are risks associated with such a long human mission in space. There are physiological problems caused by reduced gravity. Our muscles become weak and our bones become brittle. Then there are psychological problems. We've been all isolated because of COVID, and probably we had the big units and the garden. Well, if you go to the moon and Mars, think that you share small space with another 6 astronauts, 7 astronauts. The habitable zone is 7 meters. It's a cylinder, 7 meters in diameter, 7 meters in length. Okay, so there are problems because of psychological problems. Then there are acute and late risks caused by exposure to radiation, and this is where my research sits. Which is the radiation that is of concern for human beings in space? Well, we have protons, so consider atoms, strip off all the electrons. If you have an atom of hydrogen, okay, and you will remain with a proton. So we are concerned with protons. Helium nuclei, I'm a physicist, I call it alpha particles, okay? And then we have heavier nuclei. We have carbon, oxygen, silicon, nuclei, iron nuclei. So these are of concern for our health. There are 2 main sources of radiation. Solar particle events is the first one. Solar particle events are emitted mostly during solar maxima activity. They have a cycle of about 11 years. And solar particle events are these outbursts of radiation, mainly of protons, and they can cause acute radiation effects: nausea, vomit, worst case scenario, death. Okay, if the solar particle event is very violent. The problem of solar particle events is that they are not predictable. And then the second source is galactic cosmic rays that are this background that is in the universe. And these galactic cosmic rays are 75% protons, about 25% alpha particles, and then about 1% for heavier nuclei. They are more intense as solar minimum activity. So why? Because when there is a solar maxima, you have to think that you have this outburst of radiation from the sun that swipes out, okay, little bit, all these galactic cosmic rays. So when you have a solar maxima, you have more solar particle events and less galactic cosmic rays, and then vice versa for the solar minima. And the galactic cosmic rays, they increase the risk of cancer, of diseases to the central nervous and cardiovascular system. On Earth, Don't worry, we are safe because we have our natural geomagnetic field that protects us from these very harsh radiation environments. The magnetic field protects us, shields us from this incoming radiation. Instead, when we are on the moon and also Mars, well, there is no global magnetic field. So you are exposed to these harsh radiation environments if you were an astronaut there. Of course, radiation causes damages also in microelectronics, but here today I will focus on astronauts. There is also a big problem connected with not having a global magnetic field. That when you have galactic cosmic rays that are incident on the surface of the moon or Mars, they can produce nuclear fragments. They go through nuclear interactions and they produce a secondary radiation field, which also can have harmful effects in the astronauts. How do we study the effect of radiation, of cosmic radiation in astronauts? Well, we do it at DNA level. The DNA is the target that we study. This picture shows to you the basic mechanism of radiation damage, radiation damage to the cell. We physicists are simple people and we try to simplify, okay? So this is very simple scheme. Radiation can interact directly with the DNA strand and break it, or can interact with the water molecules, produce free radicals, and these free radicals break the DNA. We have the so-called double-strand breaks that happen when we break the DNA in 2 points and we produce these fragments of the DNA. The more double-strand breaks we have, the more the cell is damaged. This means that we have a higher probability that the cell will mutate, eventually to cancer, and if we give enough radiation dose, actually we kill the cell. I will report here an experiment of NASA that shows the problem of radiation protection of astronauts. They irradiated mammalian cell populations with gamma rays, and these green spots represent the double-strand breaks. And you can see that the double-strand breaks are sparse in the nucleus of the cell. But in the moment we irradiate the mammalian cells with the silicon iron nuclei that we see in the space radiation environments and not in the Earth environment, you can see that the double-strand breaks are more clustered. They follow more a track like this. So we say that this damage is more clustered, and I tell you something, this damage is a lot more difficult to repair. Of course, we have a better biological knowledge of the radiation damage to cells in the environment of the Earth. We have data that come from nuclear bomb survivors, nuclear accidents, survivors of cancer that went through radiotherapy treatment, okay? But we do not know, and there is a big gap of knowledge about the radiation, the cosmic radiation effects, because we are not exposed to this radiation in our everyday life. So there is a lot of research in this field, and I do research in this context. So are astronauts in trouble if we send them to space? NASA uses as a reference the National Council on Radiation and Protection and Measurements, report number 98, and where it said that it's okay. I mean, this is the limit, that astronauts during their career, they should be exposed to an amount of radiation that produces at max 3% of excess lifetime risk of cancer death due to exposure to radiation. Okay, over their career. But astronauts, based on our current knowledge, well, they could reach these limits in a mission to Mars. When you are in open space, going towards the moon, keep in mind that astronauts are exposed to about 10 chest X-rays per day. Now, of course, if you go to do a chest X-ray, the image is taken in a burst of radiation, isn't it? It's a very quick procedure. In space, the radiation is not just given in a burst, is given in a day, with a longer exposure. Okay, so it's also different how the damage is produced, because cells respond differently if you give radiation in one burst or over a longer period of time. And there's been this very interesting paper of Chancellor in 2018 that said maybe this limit of 3% is not conservative enough because we do not have enough knowledge of the biological effect of cosmic radiation in human beings. Maybe we overestimate the number of allowable safe days in space. What do we do about it? Do we send astronauts in space and we see if they develop superpowers? No, you wouldn't like to do that, isn't it, if you were an astronaut? Well, we do research around the world to investigate the space radiation environment, its interaction with matter, with the biological medium. We have to develop radiation monitoring systems, shielding solutions, develop models that predict the radiation doses to astronauts in different mission scenarios. And these experiments are usually done on Earth in facilities like this, the Brookhaven National Lab in the US. So we have high energy particle accelerators, and they are used to perform research. But the problem is that there is no facility on Earth that can reproduce the complexity of the space radiation environments. There are certainly experiments on the ISS, and we have also missions on the Moon and Mars. But as you can imagine, these measurements are sparse. So what we do, we use radiation physics simulations. These are softwares where we can study, we model the particle interactions with matter, and we can study the effect of radiation in detectors, in human beings, in organs, in cells, like in this example. And it's more than 20 years now that I contribute to develop to a specific radiation physics simulation tool, which is called GEAN4. The development is based at CERN. And we are about 140 people that develop this code that is used from high energy physics to space science and medical physics. And when I started my PhD and my master also, I was part of the team at CERN to extend this tool that was born for high energy physics at CERN to medical physics applications. Well, you can download it, it's for free, and it's open source. And we use radiation physics simulations in synergy with the experimental measurements. Okay, now I will report some studies that we do in our center, the Center for Medical and Radiation Physics of the University of Wollongong. Well, first of all, we modeled the International Space Station, in particular the Columbus module, and we model its real structure at the correct altitude, and then we model the galactic cosmic rays and solar particle events. And we study passive shielding solutions. What does it mean? If this is the structure, let's say I see the Columbus module in a cross-section and appreciate my drawing creativity and capabilities. I'm very sophisticated here. And we have a radiation that is incidence on the Columbus module. Well, then I study shielding solutions. So I just add the material so that I can block the radiation. So this is what we do. When we do radiation protection, we just study shielding solutions. We chuck in this piece of shielding and we stop radiation, isn't it? This is the goal. But in space, there is a big problem, and I will show you here why. Let's suppose that this is a galactic cosmic ray proton that is incident on my Columbus module. It passes through, yes. But because it's a high-energy particle, produces a shower of secondary radiation. We will have gamma rays usually come from nuclear excitation, neutrons, we have alpha particles, aluminum nuclei, so heavier particle nuclei. So we have a complex secondary radiation field. The problem of radiation protection of astronauts in space is that even if we study shielding solutions, yes, we can stop a little bit the incoming radiation, but we need to find a shielding solution that limits the generation of this shower of secondary particles, because this is also harmful. And research, and also mine, showed that if we use polyethylene as a passive shielding solution, this is effective in reducing this generation of secondary particles. Polyethylene, you find it in your grocery bags and your plastic water bottles. Okay, that is a nitrogen-rich material, and they are more effective than, for example, aluminum, to reduce this secondary radiation field. So we say that sometimes in space it's better not to have shielding than having shielding, okay, because of this generation of this secondary radiation field. Then we had our anthropomorphic phantoms, where we model astronauts in all their organs and tissues inside the Columbus module. Of course, the simulations require long execution time, so we use the National Computing Infrastructure in Canberra. And when we develop a simulation tool, well, we need to understand how accurate it is. When we use it to calculate the dose of radiation to astronauts, how accurate it is. Because, you know, this simulation produce some numbers, but how reliable are these numbers? So a big, huge activity that we do in development of computing physics simulations is to compare the simulation results against experimental measurements. And in this case, we compared against the measurements done in the Matryoshka experiments, where this mannequin was flown on the ISS and detectors were set in different locations. And then we compared our simulation results against the experiment, obtain a reasonable good agreements. We calculate the dose. The dose is the amount of radiation that is given in a specific organ divided the mass of that organ, and it's measured in grays. This is the only information of physics I will give to you. So 1 gray is joules, because it's energy, divided by mass, so it's kilograms. Okay, this is gray. So this is milligray per day. We calculate the dose in different organs. We are especially interested in the eyes because of the risk to damage the cataract, for the cataract. Then bone marrow because of leukemia, risk of leukemia, brain, because it's very important, the brain, the hearts, the genitals because of possible, mutation of the genes in the progeny. Here, these are results of our PhD student, Matthew Large. And these are some results we got, and we found, when we consider the trajectory of the ISS, we were just on top of the South Atlantic anomaly, where there are more, let's say, there is more radiation there. And so we found that these trapped protons that are in the South Atlantic anomaly, it's a specific region of the Van Allen belts. So these produce more dose, and then we have galactic cosmic rays, the protons that produce the higher dose in the astronauts. But again, we use this case of the ISS just to compare to experimental measurements, to understand how accurate was our model, and we were satisfied with the agreements. Now, a concept of vehicle to study is this inflatable balloon. In this concept of transfer vehicle to Mars, we have a rigid internal core. And then we have this inflatable balloon made of different materials, including hydrogen-rich materials, and had to quantify the shielding capability of the inflatable balloon. And what I found out that even if I double the polyethylene passive shielding thickness, Well, I just, if I double the shielding, I have only just few percent difference in the stopped galactic cosmic ray protons. So even if you add more shielding, it doesn't change much the situation. This happens because galactic cosmic rays are very energetic. So it's very energetic, they just pass through, okay, the shielding. So to use these passive shielding solutions are not very effective for galactic cosmic rays. But instead, they are effective for solar particle events. In particular, I had to study how thick must be this rigid water wall that protects the astronauts in the case of a solar particle event. If there is a solar particle event, the astronauts have to recover inside this region. And I found out that the 75 centimeter water equivalent wall stops almost all the solar particle events. For galactic cosmic rays, as I told you before, the passive shielding it can be considered as the only solution. And there are groups in the world, not me, but there are groups that study active shielding solutions. That means to use magnetic fields surrounding the transfer vehicle that they deflect particles. Here you see a cross-section of a transfer vehicle. These are solenoids that produce the magnetic field. And you can see that the incident galactic cosmic rays, they bend in their trajectory. And this is what a magnetic field does, isn't it? It bends and deflects the particle. And this group, these results of Ferrone and Cry of the Texas MD Anderson Cancer Center showed that we can, if we have a magnetic field of about 7 Tesla, which is significant, okay, because in MRI we have 1.5 Tesla. Okay, so 7 Tesla, we can protect the astronauts following the current career limits of NASA. It's still far away, this solution, because it's very complex, but it's something that is studied. Now, let's look at the moon, because the moon is closer, okay? So we focus on the moon. Also because we have a project with the European Space Agency on the moon. So this is why we focus on this. We calculate again the dose in different organs in our Phantom that reproduces the astronauts. We have both female and male astronauts. Okay, and again we calculate the dose in the various organs due to galactic cosmic rays. But now we do something more, and we are the first ones in the world that we do this, okay? What we do, if this is, we calculate the dose in the entire organs of the astronauts, but in our multi-scale approach, we also study the effect of radiation and nanoscale in the DNA in the various organs. So we try to connect, to go from those in organs to see what happens at the level of DNA, and then I will tell you what we like to do. But this is the first time that something like this has been done. And we calculated the number of double-strand breaks in various organs, and we found out that about 30–40% of the double-strand breaks is due to the lunar backscatter radiation. So not only, so we have to consider the incident galactic cosmic rays, but also all the radiation that is generated by the galactic cosmic rays when they're incident on the Sun and the Moon, and this radiation comes out, let's say, towards the astronaut, that produces 30–40%. So we need really to study in detail the mission scenario. And now our next challenge is very challenge. This is a 10 years challenge, okay? Is to connect this calculation of the early DNA damage to the biological effect of cosmic radiation with simulations. And this will help us to cast more light on the, on what is safe for the astronauts. This is my last slide. We also study shielding solutions on the Moon and Mars, okay? We call them planetary shielding solutions. And one idea is to use bricks, sort of regolith bricks, and build this habitat, and the astronauts go in there. And I mentored the student, Yulia Akisheva, of the Isai Superhero Institute of Toulouse in France. She's a PhD and she works within a project of the European Space Agency. And we study shielding solutions on the moon. And in particular, bricks of material that is similar to the regolith. And we found out that we can obtain similar radiation protection to the ISS if we have a thickness of 40 centimeters of compressed regolith on top of the head of the astronaut. So if these habitats, they have walls that are at least 40 centimeters thick with these specific bricks of regolith that has been compressed, well, we obtain a similar radiation protection of astronauts than on the ISS. So that's all. I would like to pass the message that radiation physics simulations are software tools, and they really support space research. They really help to solve design problems before developing the technology. They help to save up a lot of money. They allow us to model, of course, in certain degree of accuracy, the complex radiation field that we find in space. And let me say that why is important to go to Mars? In my point of view, it's important because we are explorators. Isn't it? We are humans, we love this challenge, but also think about the repercussions that this research for Mars brings to our life on the Earth. In my specific research, all this research that is performed has impact also on the cancer treatment performed by means of radiotherapy, in particular proton therapy that will come in Australia in the next couple of years in Adelaide. Okay? Thank you very much.
So I'm Ian Wolfe. I do a weekly science and technology podcast and community radio show, Diffusion Science Radio. If you go to the website, you can listen to interviews with all of these people in the last 4 episodes. And in a conversation, sometimes they'll give you some thoughts and some information that might not have got into the talk. So with that in mind, I'd like to start by seeding some questions, and then I'll go to the audience, and someone will come round to you if you put your hand up that you want to ask a question. So, a question that was put to me in the break, Professor Boy, if we've got aerosol viruses and bacteria and everything else in the atmosphere, particularly viruses that aren't alive and aren't dead, how long can they stay up there and just move all around the world before they're not a problem anymore?
Don't know. Look, the oceans are teeming with viruses. The air is teeming at a lower concentration. They, in order to propagate, in order to procreate, they do need cells to inhabit and take over the machinery of, so they don't have their own machinery for reproduction, they have to take over a cell. But you know, the great majority of these viruses are just fine. We interact in a simple and non-pathological way. And medicine and people like me concentrated on the ones that cause trouble. And someone asked me about Menangle virus, and it's only actually known to have infected 2 humans and a lot of grey-headed flying foxes. And so then I read about a related virus called Hendra, which some of you may have heard of it. It's killed 2 humans and a few more have been sick. and in one outbreak in Hendra, Brisbane, it killed in short order within a day a dozen horses. So it was highly transmissible and highly. Reminds me a bit. I'm going to talk too much. Reminds me a bit of The Last of Us. You catch this fungus in your brain and you're a zombie within 12 hours after a bite. Viruses don't really do that.
Thank you. So, Anna, if I could ask you the question that you seeded in your talk, if you could tell us a little bit about knots, and was it the Jones problem?
Yes, originally I wanted to speak about this in my talk, and then I realized it was too long and I didn't have time, so I planted a seed instead. And this is just another beautiful example of categorification. And it's an example that is perhaps more powerful than the one I gave. So I talked about knots and how this is a mathematical world that we study. And knots have this really mysterious invariant called the Jones polynomial. And this is a way that you can attach a polynomial to a knot. So something like 1 plus t squared plus t to the fifth. And this polynomial is really interesting because it's not obvious what it's measuring. Already we saw this in the Euler characteristic. It wasn't so obvious what this was measuring about the topological surface, but the Jones polynomial is even more mysterious. It's really not clear what it's measuring about the knot. But sort of recently there's been found to be a categorification of this in something called Kovanov homology. And with this categorification, suddenly it's more clear what the Jones polynomial is measuring. And this tool of Kovanov homology is really useful in other fields of mathematics. I was actually going to plant a seed for a talk that's happening at the University of Sydney next month on the four-dimensional Poincare conjecture. And this talk, it discusses how this tool, Kovanov homology, which arises via categorification, is actually a really promising tool at the forefront of this area of maths.
Okay, I've got a question for everybody. So, Anna, the Earth is protected by a magnetic field, but it's a very weak magnetic field. But it took 7 Tesla to protect the astronauts. Why is the difference?
Yes, thank you. Yes, the field on the Earth is a lot weaker, but it's action, not to say the distance, the action, no, it's a lot longer. So it's yes, let's say that the action is on a longer distance. Instead, if we develop an active magnetic field, let's say active shielding on a transfer vehicle, this magnetic field will have a shorter action in terms of distance. It will just be around the space vehicle. So we need a stronger magnetic field. Okay, it's not just the intensity of the magnetic field, but also the space where this magnetic field exerts the Lorentz force on the charged particles. Hopefully I was clear.
Thank you. And David, so do you have to be an analytical chemist if you want to play with mass spectrometers?
I'm a physicist.
Well, I got asked a question about the properties of the plasma before, and sorry, I couldn't answer it. You're better off asking her. Because the people who design and develop them, they're all physicists, correct? But to use them these days, so I mentioned in my talk that you can go to any environmental laboratory, any clinical path lab, they all have them. The majority of people using them there aren't analytical chemists. The vendors have done a very good job of basically simplifying how the software works. So when I first started, you had to understand how different components worked. Now, so the vendors done a very good job at removing that complexity. But then, as a counterpoint, when something goes wrong, those people don't know what to do. So, you don't have to be an analytical chemist, but it helps.
Yeah.
Thank you. So do we have our first questions from the audience? Is anyone... Oh, there's a hand over here. We can... Over there. It's the first one I saw.
Okay.
Hello.
My question to Professor Boyd is, how does viruses penetrate cells and divide and increase numbers very easily inside the cells?
Great question. Viruses on their outer surface have spikes. So COVID has a spike protein. Influenza has different spikes called H and N. Varicella zoster, which causes chickenpox, has an E spike. All of these spikes which stick out help the virus to connect with a cell's receptor. And a receptor is something that a cell has which sticks out, which helps it to receive messages from other parts of, say, the body. So the cell receptor, for example, a thing called ACE, the ACE receptor combines with the protein S of COVID, and then that connection allows the virus to get in, and then the virus very cleverly takes over the machinery of a cell to convince the cell to make virus and not the proteins that it normally makes. So one cell can then make hundreds, if not thousands, of viruses, which then have something in their mechanism which help them to get out. So flu has two different spikes, one that gets it in, and the other one, called neuraminidase, which helps the virus to get out. And then it goes and finds another cell in your lungs and does the same thing all over again. So there's little receptors, and they're all proteins really. So the virus, lock and key mechanism, it's got a lock, and it unlocks the key to a cell and gets in and takes over.
Thank you. And we've got one over here.
This is a question to David Bishop. When I did analytical chemistry at Uni of New South Wales 60 years ago, it was as dull as dishwater. And yet, when I actually had to use analytical chem to study things like particular compounds, molecules that were in, for instance, cigarette smoke, it was utterly fascinating. I would hope that after your talk that things are totally different now, and analytical is the queen of the sciences rather than organic or inorganic, which is what most people used to fall in love with.
I would hope so too. So I think, so it obviously depends on the university you're at. So at my university, it was mentioned in my bio there, I've introduced a master's focusing on analytical chemistry technologies. Basically, of course, especially if you're living in Sydney and you want a job in chemistry, it's pretty much analytical chemistry. There's not too many synthetic chemistry jobs available. There's not too much inorganic chemistry jobs available. But if you want to go and, there's some very giant commercial laboratories out there doing analytical chemistry. And I agree. So, and we focus on hands-on learning. So that's where, actual practical skills, because that's what's, I don't work at these big commercial laboratories, but that's what they need, right? And also, if people then want to go and do research, it's better off knowing how to do something rather than, you can always look up theory later.
We've got one down there.
Cool. G'day. My name is Arfin. My question's for Professor Susanna Guatelli. Wonderful talks, everybody. This is very interesting. So one of the coolest things that's happened in the past few years or longer is the commercial growth in space.
Yeah.
And so there's all these companies, startups like the ones everyone and I work for, who are looking at long duration voyages and all the unsolved problems there. It was awesome to see the kind of human factors challenges, but also the radiation challenge you talk of. A lot of companies are trying to plan these voyages, but they don't really necessarily understand the radiation impacts. Do you see your work evolving into kind of like a mission design as a service or having any application there?
Yeah, oh, this is a very complex question. I will try to answer based on my experience as a researcher in Australia. Okay, so okay, where do we start from? Oh yes, so then we talk about radiation protection in research is 20 years. I mean, I started with my PhD, okay, and radiation protection was always there, but it seems to me that the problem a little bit was a little to find there was not there was not a connection between the research and the company, you know, that develop satellites, telecommunication systems, and so on. While there is, for example, in another field that is the study of the effects of radiation and damages on microelectronics. When we talk instead about space radiation protection, there is not this connection, and in my point of view, I have to say that it's good that nowadays in Australia we have the Australian Space Agency, because now they provide that environment that probably will help us to bridge this gap. Because, for example, I would love to apply for grants in Australia in this field, that is radiation protection of astronauts, but I don't know how, I don't know how, where, because it's research and it's not too much, let's say, it's not too commercial now, so that is a problem for some grant scheme. While instead the Australian Space Agency, the Australian government are trying instead, they are injecting, they want to create momentum in terms of industry, okay? So I am in this dilemma, let's say, in this problem, that I do something that is very research, and we have to understand how to bridge this gap, to bring the companies and the researchers to collaborate, and I would love to continue this conversation with you guys.
Fantastic. And we're still on this side of the room, and there's some more over here.
Question for Anna Romanov. I was very interested in your talk in terms of exploring equality. Got two questions. When does equality sort of disappear out of mathematics and reappear in philosophy? If that is a question that's interesting to you. I was also interested is there a very active field in research in the does not equal sign, with the one with the little stripe through it? Thank you.
Thank you. I like both those questions very much. Unfortunately, I don't really have great answers to them. I'm not. It could have become a philosophical question pretty quickly, but I'm not sure at what point it departs. So as mathematicians, we like to sort of make concrete rules and then play by those rules. And so in any mathematical world, we decide from the beginning what equals means, and then we go forward. And this question of the decision, when we decide, this is kind of laid out from the beginning. And then for your second question, I also don't know. I think it's once we have a notion of equality, then there's always that thing not holding. And if it doesn't hold, that's the definition of that symbol. But this would be an interesting prospect to see if there was more subtlety there as well. Maybe we're more interested in things being equal than being not equal.
Thank you. Oh, and we've got one at the back where the microphone is.
Right. With mature physics, what I like to see is precision. And I think with neurological disorders, it takes a long, long time to define them as to what they are. Now, a statement was made that with some of these processes, you can get good correlation between the measurement and the diagnostics of the doctor. I would think that that means that you can go straight into the measurement and diagnose a lot quicker. And the other question related to that is, if you've got a good pattern that you can produce from a measurement of someone's problem, I would presume that you can therefore compare various diseases that are on the same spectrum and find the variations and maybe improve the treatments? Thank you.
Thanks for your question. There's a couple of problems there with the technique I'm using. For starters, we need to get the brain out of people. People don't like it to give it to us while they're still alive. But it's I see where you're coming from. We are working, so we've looked at Parkinson's disease, we've looked at multiple sclerosis. We are starting a project on motor neuron disease as well. The goal is we want to understand what's going on. And once we're still trying to understand what's going on. Once you get to the understanding stage, then you can go, all right, what comes next? If we can figure out what's taking those metals there, if it is related, then you can go for diagnosis and treatment. We're still at the understanding stage. It's still very premature. There's still so much which is not known about neurology. The human body is incredibly complex. I'm an analytical chemist, right? So I'm not going to pretend to be a biologist. I work with a pathologist who is a practicing pathologist at RPA with this work, and he's always fascinated by what we find. And I did say that there's clear, what we've seen, the data is showing, we are seeing these metals again and again and again in these neurological diseases. We've also seen them in cancers as well. We've seen mercury present in breast cancer and in prostate cancer. Prostate cancer. So now we can't say if the metals are there as a causative agent or are there because something else. It's a reactive process. So we don't want to leap to speculation. What we can say is they're there. So I'll leave it to a medical doctor to be able to.
Would you like to?
I just happened to be speaking to a neurologist who's an expert in Parkinson's disease this afternoon, and I put to her, what about the DAT scan, which people do to diagnose Parkinson's, which D stands for dopamine, which become a neurotransmitter, a signaler in the brain, which becomes decreased in certain parts of the brain in Parkinson's. And her simple answer was, it doesn't direct my therapy. It doesn't make me certain whether it is or isn't Parkinson's. It's helpful, but not definitive. It has issues with being sensitive and specific. Does it diagnose what it's meant to? Does it diagnose what it's not meant to? So this is a dilemma in medicine. We do tests all the time and we do too many. And we spend too much money on chasing rare things. And so getting a good test is a good thing.
Okay. Oh, we've got one at the back here.
Hi, wonderful talks from all of you. I have 3 questions for 3 of the speakers today. I will start with Professor Board. So you were talking about this COVID and all the pandemic issues, and that it goes and there is a mutation. So it happens one from another, and then it mutates, it becomes a new generation of disease. And you are also talking about, I think, 4 times of using of the, what's that called, the vaccination, yes. So I was thinking why this is 4 times and why this is not like, or is there a chance that we have to do it for every year once, because they're mutating and they're generating new things that we don't know what will be.
Let me answer in fairly simple terms, because I like to think in simple terms. We've gone through the Greek alphabet and we've missed a few along the way. And what we've essentially had is every 6 months for 2 years, a new variant that escaped immunity to the old one and therefore infected new reams of people. For the last 16 months, we haven't really had a new variant. We've had subvariants. We've had variations on the theme. But as virologists are stating, it's not different enough to cause major disease, but different enough to evade immunity and to cause new outbreaks. So we've had 4 different peaks in the last year and a bit of Omicron. Each one has been less. And that then leads me to my second explanation, which is that although it's evaded immunity, it's done so less well because each peak in numbers has been less. And the death rate has also gone down. The death rate for the first 2 peaks was very high. 15,000 Australians last year is a lot of Australians. The great majority of them were over 80 years of age, by the way. And to your third part of the question, how often should we chase this virus? Less often, and just like flu, once a year should probably be enough, and that's what I've been recommending for a while. At the same time as flu, and there'll soon be a vaccine where it's mixed in the same syringe, and that's been developed. It's being tested at the moment. And if I'm allowed to say one more thing, coronavirus and influenza virus are both RNA. They're very simple in some respects, but coronavirus has a check enzyme called a polymerase, which does ensure that its progeny are more like the parents than the progeny of flu. So flu mutates faster, and we only vaccinate newly for that once a year. So I can see us probably getting very quickly to the stage of only having a new booster for corona once a year.
Just to add to this, I had gone through parainfluenza and influenza last 2 years, once a year, and coronavirus only one time. And coronavirus thing was the one, the COVID, I felt like nothing happened to me. And the parainfluenza, I thought I'm gonna die. Anyway, my next question is to Anna. So you were talking about, my question is almost the similar thing that the other person asked. What about, when you were talking about the equal sign, what about the equivalent sign, and what about the nearly equals to sign?
Oh, you mean the other shape, so it's sort of the squiggly equals. I could have used any of those signs, really, I should say. There's nothing especially special about the straight-lined equality. In fact, usually in mathematics, what we would use is a straight line with a curly line on top. That's our normal thing for isomorphic or homeomorphic or any of these words that mean equals in different settings. So the symbol itself is not quite as important. It's just the notion of equality. And we're actually not consistent as mathematicians. We change our symbols in that context all the time. Sometimes it's one squiggly line, sometimes it's 2, sometimes one straight and one squiggly. It's a little bit frustrating if you're a student.
Thank you. And the last question is for Professor David. You were talking about the Parkinson's disease and the finding mercury at a particular point of our brain. So could you please tell a bit more about it, like how much mercury and which part of the brain, and if we can know a bit more?
So the part of the brain where mercury was found amongst all samples, so that was people with Parkinson's, people without Parkinson's, and people with known mercury exposure, it's called the locus coeruleus. So again, I'm not a biologist, but it's my understanding it's at basically where the brainstem in the brainstem, so entrance into the brain. So all samples we analysed had mercury there, but the Parkinson's people, that's where we found mercury in substantia nigra. We were hearing about dopamine there, the dopamine cell death. It occurs in substantia nigra. We only found mercury there in the Parkinson's patients. There's a few other regions of the brain, pontine facial neuron and the lateral geniculate nucleus. Yes, so I'm not a biologist. I'm not going to pretend to be. The regions of the brain which were directly impacted by cell death in Parkinson's, we found mercury there. We did not find mercury there in the other samples, including people like one of our controls is someone who injected themselves with mercury for 6 months. So we know that person had mercury in their system. Positive control. So yeah.
Okay, we've got one over here.
Yeah. Hi. First, I would like to say that the company that I work for has a value which says you should not be the smartest person in the room, like for any meeting. So I can say that I'm living the value today. So by all that. So I loved every talk, and this is the first time I've attended this forum. So thank you, all of you. My question is more of an engineering, and I was talking to Professor David earlier, is that, in the mass spectrometer, there is a plasma, and obviously it's really, really high temperature, and the surface of the sun probably vaporize almost every material that we have on Earth. So why doesn't the whole apparatus not just vaporize with that?
Yeah, so thanks for your question. So the plasma is very well controlled. There's a defined radio frequency coil which produces the energy required to ionize the argon. There's a high flow of argon surrounding the torch where the plasma is produced to keep the plasma confined to a specific region. And then when it hits only the very tip of the plasma, which is the coolest part of the plasma, hits the actual interface of the mass spec. So it needs to actually touch it to create basically a vacuum, so we don't get outside stuff coming into the mass spectrometer. And that is either made of, actually, metals like platinum or nickel. So platinum's actually quite soft, but it's water cooled. So it's flushed with water, which is temperature of 4 degrees. That flow has to be quite high to make sure that the interface to mass spectrometer stays quite cool. Thank you.
Well, just a question for Susanna.
Yeah.
In relation to the trip to Mars.
Yeah.
And there's a potential, I understand, by utilising new propulsion methods to reduce the transit times by up to 75% of less than what it is now.
Okay.
I think using nuclear power. But have you heard any rumours to that effect? And
No.
is it likely to happen?
Sorry, this is not my field of research, so I'm a little bit. I know there is a lot of research in that, but I would not feel to comment. I'm not an expert. Sorry.
Just another question to Professor Boy in relation to mosquitoes. You haven't mentioned mosquitoes as a venue for transmitting viruses. Is that correct?
Oh, absolutely. Oh, absolutely. There's a whole bunch of diseases that are currently a major concern in Australia, like Japanese encephalitis, Murray Valley encephalitis, which are transmitted in the environment because we've suddenly got lots of still water in southern for extended periods and the temperature is warmer. So the mosquitoes love the water, and then they bite the macropods, the wallabies, in which the virus then accumulates. And then there are mammals which get bitten, like horses and pigs, which massively amplify virus. They get much higher levels of viremia. And then when they get bitten by mosquitoes and they're in close habitation with humans, piggery workers, horse trainers and the like, they can get these nasty viruses that formerly were only in the very north of Australia. Murray Valley encephalitis, although it's named after the Murray Valley, is mainly in northern Australia. Japanese encephalitis used to never go past Cairns if it was lucky. It's usually in the Torres Strait Islands. And suddenly, in the last 2 years, these viruses are all down the east coast and over to South Australia, and a real concern. And it could be because we've had La Nina for 3 years and a lot of water and a lot of mozzies, and the mosquitoes are crucial. Can I just say that that question about going to Mars, the Epstein Drive, haven't you seen the TV series?
And we've got a question here.
My question is to Anna. To what degree of certainty can you say things are equal? So there's some uncertainty, I guess, and there's the concept of the known unknowns and the unknowable unknowns and all those sorts of things that which may fit into that answer. So yeah, I'm just interested if you've looked at that sort of end of equality.
Yeah, so one lovely thing about pure mathematics is that we don't deal with the physical world. And so since all of these ideas are sort of concepts in our minds, if we declare our notion of equality to be for topological surfaces or something, that we can continuously morph one into another to show that two things are equal, we have to find some way that we can do this. But once we find it, it's there. So there's not this issue of sort of measurement uncertainty in the realm of pure mathematics. So we know things are equal if we can find sort of an equality map between them, which takes us from one to the other. And this is something, if we were actually physically making the spheres or the knots, this gets a little bit more subtle because you can ask questions, at least with the with deforming things, you sort of have to take measurements. But since all of this just is happening in our heads, we have a pretty concrete idea.
Okay, we're getting close. We've got one over here.
Another question for Robert Boyd. The pandemic has made me think how important the job of epidemiologists are. And I read this quote from a notable virologist in the history of virology in America, Hans Zinner, and Zinzer, I should say. And he was a soldier in the First World War. And he said that soldiers have rarely won wars. They more often mop up after the barrage of epidemics. And typhus, with its brothers and sisters, plague, cholera, dysentery, has decided more campaigns than Caesar, Hannibal, Napoleon, and all the inspector generals in history. How much have soldiers mopped up afterwards, considering that the Spanish flu came kind of towards the end of the First World War? And how much do you think that the whole course of humankind has kind of been more driven by epidemics than war?
You're probably right. I mean, during the war, the Great War, there was trench fever, there was, walking through and they were losing their legs to infection. There was salmonella, cholera, typhus, I think you might have mentioned. There was countless diseases killing people at the front. So, yeah, I concur. Oh, and epidemiologists are just amateur mathematicians. They'd like to be in a better place, and one day they'll be mathematicians.
Okay, so do we have another question, or is that we have room for? No, we don't have another question. All right. Oh, so we're moving on to the next.
There is a question here. Sorry, correct?
We've got an urgent request.
Yeah, thanks. A quick one for Anna. In your topological mathematics, is there a role for multivalent logics? Do you have things that are not just equal or not equal, but you've got multiple yeses and nos? Do you have a multivalent logic role in topology?
Not that I know of in topology, but I could certainly imagine this having a place in other areas of mathematics. I mean, especially in logic, which in some sense is an area of mathematics. But I couldn't imagine how it would manifest in topology. It's sort of an interesting question. Maybe it's something to dream about.
I thought you should have just answered, I'm afraid not.
Missed opportunity.
All right. Oh, and now we've got a few words here from Jonathan. Jonathan, do you want to stand up? What would you like to see?
I'd like to stand up.
All right, Jonathan.
Hello, my name is Jonathan. I am 9 years old and I go to school in Parramatta Public School. I'd like to say as much as I can about what I know in human space flight. So the first mission I'd like to talk about is the Artemis 1 mission, launched by NASA in September 2022. SLS, or Space Launch System, was launched in September 22 and went into orbit after 10 minutes after launch. When the first stage that will be jettisoned is the boosters. That boost the speed of SLS for 2 minutes until they are jettisoned to land in the ocean. Next, around 8 minutes into the flight, is the core stage. The core stage will keep firing until we are in the upper atmosphere of Earth. Then they will jettison and leave the cryogenic propulsion system, interim cryogenic propulsion system, or ICPS. The ICPS will fire for about 2 minutes to get out of the atmosphere, and then fire for another 4 minutes to get us out of Earth orbit. After Mission Control has given the signal to leave Earth orbit. Then afterwards, it's going to fire a short burn that will give it speed to get out of the Earth's sphere of influence. And then afterwards, the ICPS will be jettisoned to leave the spacecraft on its own. The spacecraft will have a journey of about 2 days until it reaches the moon's sphere of influence, when it will slow down to go into a stable orbit around the moon. When it's in a stable orbit, it will change its orbit by putting it into an elliptical orbit that at one point will get really close to the moon, and then at another point get really far. For future missions of Artemis, there's going to be a lunar gateway, a lunar station called Gateway. In those next missions, Orion will dock to Gateway. Then it will. The astronauts that are assigned to go down to the moon will transfer into the lunar lander, whereas the astronauts assigned to Gateway remain on station. Then the astronauts that are assigned for the lunar lander land back on the moon, and after a significant period of time, they will return back to Gateway, when all those astronauts will go back into the Orion spacecraft. Then it will jettison and head for a course towards Earth, pulling up a few burns on that 2-day trajectory. Afterwards, when it reaches Earth's atmosphere, it will slow down again, and it will jettison from the service module. Then it will point to the Orion. The Orion heat shield will be pointed towards the atmosphere. Then, as it re-enters, once the heat and plasma that forms on the heat shield as it goes through the atmosphere at extremely high temperatures and speeds, Mission Control will lose communication with the spacecraft, because no energy, no form of communication can go through plasma. During the upper atmosphere, the first chute will deploy, slowing the spacecraft down. Then the drug chutes will deploy, slowing us down again, and main chutes deploy to slow us down to 20 kilometers per hour for splashdown. Other facts for Orion equal that the Van Allen belt that Professor Susanna said, we're going to have to pass through that belt twice. Once to get to the moon and once to go back. Then the heat shield for Orion is actually the biggest heat shield ever made on NASA spacecraft. And also the ESA also helped on creating the service module for Orion. Thank you.
Thank you, Jonathan.
Well done.
So, thank you very much for your participation tonight. Same time next year? Right? Okay, same time next year, same place. And have a very safe weekend and enjoy yourselves. Thank you.